There is a fault hiding just offshore from the western United States that has gone more than 3 centuries without producing its biggest kind of earthquake. And, strangely enough, the part that worries many experts most is not necessarily the earthquake itself. It is not even the tsunami, although both the shaking and the wall of water could be catastrophic. The deeper concern is what begins happening after the ground finally becomes still. Within the first couple of hours, a chain reaction could unfold across the Pacific Northwest that the earthquake merely starts. Massive petroleum tanks could rupture almost simultaneously. A fuel release comparable in scale to a major oil disaster could pour into a river running through one of America's largest northwestern cities. That fuel could ignite. A moving river of fire could travel through Portland. Industrial facilities damaged by the same shaking could release toxic chemicals into the atmosphere. A poisonous plume could begin drifting toward neighborhoods whose residents cannot escape because highways, bridges, and local roads have already failed. And the firefighters, paramedics, utility workers, and rescue crews expected to contain that disaster would be trapped inside the same broken transportation network as everybody else. Some hydrants could have no water. Fire engines could have nowhere to drive. Mutual aid crews from surrounding communities could be dealing with their own emergencies. The earthquake is coming eventually. That is the fundamental geological reality scientists agree on. What nobody can tell you is whether it happens tomorrow, decades from now, or somewhere in between. But there is another uncomfortable possibility. When Cascadia finally ruptures, the shaking may not be the part of the disaster that ultimately causes the greatest suffering. That is the side of this story we are going to examine. I am your name, and this is your channel. If you come here for deep investigations into real natural hazards and the science behind them, subscribe now. We take these subjects far beyond the headline every week. Now let us start with the fault itself. It is called the Cascadia Subduction Zone. It stretches for roughly 700 miles beneath the Pacific Ocean, running from offshore Northern California past Oregon and Washington and north toward British Columbia. Along this boundary, an oceanic tectonic plate known as the Juan de Fuca Plate is slowly being pushed beneath the enormous North American plate. Geologists call that process subduction. And subduction zones are responsible for some of the most powerful geological events anywhere on Earth. The same broad tectonic process helped create the Cascade volcanic chain. Mount St. Helens, Mount Rainier, Mount Hood, and numerous other volcanic peaks exist because oceanic crust is being forced downward into the mantle where heat pressure, fluids, and melting help generate magma that eventually rises toward the surface. But the volcanoes are not today's story. The dangerous part for us is what happens along the plate boundary when movement stops being smooth. The Juan de Fuca Plate continues attempting to move beneath North America, but enormous sections of the interface are locked by friction. The plates are not quietly sliding past each other. They are effectively stuck. And while the boundary appears calm from the surface, tectonic motion has not stopped. Stress is accumulating inside the rocks, year after year, decade after decade, century after century. That is the defining character of Cascadia. It stores energy for extremely long periods. A fault such as California's San Andreas produces earthquakes more frequently across different segments, allowing some strain to be released through smaller and moderate events. Cascadia behaves differently. Large portions of the megathrust can remain locked for centuries. Very little happens. Communities grow. Cities expand. Bridges are built. Pipelines are installed. Generations pass without experiencing the event the entire landscape is geologically capable of producing. Then eventually the locked boundary breaks, and centuries of accumulated strain can release during one enormous rupture. So every year without a major Cascadia earthquake should not be interpreted as another year proving the danger has disappeared. The fault is still there. The plates are still moving. The locked zone is still storing strain. When the next full margin rupture eventually occurs, estimates described in the source place the earthquake somewhere in the upper magnitude 8 range to around magnitude 9. And to understand why that number is so serious, you need to understand what earthquake magnitude actually means. Magnitude is logarithmic. A magnitude 9 earthquake is not simply a little larger than a magnitude 8. Each whole number increase represents roughly 32 times more energy release. That enormous energy difference is partly connected to how much fault actually ruptures. A smaller earthquake may break a comparatively short segment. A full Cascadia event could involve hundreds of miles of plate boundary moving in one sequence. And because the rupture is so extensive, the shaking can last far longer than the earthquakes most Americans have experienced. A magnitude 6 or 7 event on a California fault might produce severe shaking for 20 or 30 seconds. A full Cascadia rupture could continue for approximately 3 to 6 minutes. Read that again. 3 to 6 minutes. 30 seconds of violent shaking already feels endless when you are inside it. Now imagine the motion continuing through the first minute, then the second, then the third, and perhaps longer. Every extra second creates additional opportunities for weakened structures to fail. Connections break. Walls crack. Unreinforced masonry falls. Bridges continue oscillating. Pipes stretch beyond their tolerances. Electrical systems are damaged. Fuel moves violently inside storage tanks. What survives the first 30 seconds may not survive several minutes. Along coastal locations closest to the offshore rupture, ground accelerations could become extreme. The source describes short periods potentially exceeding 1 g, meaning acceleration comparable to the force of gravity itself. At that level, objects are not merely trembling on tables. They can be thrown. People may have enormous difficulty remaining upright. Farther inland, metropolitan Portland and Seattle would experience somewhat lower intensity than the coastline nearest the fault. But those cities contain something the coastal communities do not. Millions of people. Dense urban infrastructure, older bridges, unreinforced buildings, fuel networks, water systems, railways, airports, ports, and enormous quantities of infrastructure constructed long before modern engineers fully understood the threat posed by Cascadia. Some of the physical systems supporting Portland and Seattle were built before plate tectonics became accepted science. When those bridges, buildings, pipelines, and utility systems were originally designed, the people creating them did not understand that an offshore megathrust capable of producing a magnitude 9 earthquake sat nearby. Modern engineering has improved enormously. But infrastructure built decades ago does not automatically become modern simply because scientific understanding changes. And that is why a Cascadia rupture is expected to attack multiple lifelines simultaneously. The electrical grid, water distribution, fuel pipelines, highway bridges, rail corridors, ports, airports, communications. The problem is not one system failing while everything else remains available to help repair it. The concern is several major systems going down at nearly the same time. The source scenario places widespread power restoration on a timeline potentially measured in 6 to 12 months in the hardest hit region. 6 to 12 months? Keep that figure in your head. Because every additional disaster we are about to discuss occurs against the background of a region that may already have lost electricity, communications, transportation, water service, and fuel distribution. Older casualty scenarios for a full Cascadia rupture have estimated more than 3,000 deaths and economic losses exceeding $81 billion. That would already rank among the worst natural disasters in American history. But newer hazard discussions raise a disturbing question. What if those traditional figures emphasize the direct earthquake and tsunami losses while underestimating the secondary disasters triggered immediately afterward? Because one of the largest secondary risks is concentrated in a very specific place beside the Willamette River in Portland. It is known as the Critical Energy Infrastructure Hub. The name sounds bureaucratic. What sits there is anything but abstract. The hub contains a dense collection of fuel terminals, petroleum tanks, industrial facilities, pipelines, and distribution infrastructure positioned along a narrow stretch of river near Portland. And according to the source, approximately 90% of Oregon's liquid fuel supply passes through this corridor. Gasoline, diesel, jet fuel, heating fuel, industrial petroleum products, fuel supplying airports, fuel supplying trucks, fuel supplying emergency vehicles. 9 out of 10 gallons used across the state moves through this one concentrated area. If you were deliberately trying to create a single point where one earthquake could cripple an entire state's fuel system, you would struggle to design something more vulnerable. The storage tanks themselves are concerning. Many were built decades ago. Some date from before 1970. A number were constructed under seismic assumptions that experts now consider insufficient for the magnitude of shaking Cascadia could produce. But even that is not the deepest problem. The ground underneath them may be worse. This infrastructure is not sitting on strong, competent bedrock. Much of the area occupies loose, sandy, water-saturated sediment beside the river. That geology is highly susceptible to one of the strangest and most destructive earthquake processes in existence. Liquefaction. Liquefaction sounds complicated. The basic idea is simple. Ordinary soil behaves like a solid because grains of sand and sediment press against one another. Friction between those particles allows the material to carry weight. Buildings stand on it. Roads cross it. Pipes remain buried inside it. Now add water between those grains and shake the material violently enough. During intense seismic motion, pressure inside that saturated soil can rise. The individual grains temporarily lose some of the friction that normally holds the structure together. For a short period, ground that behaved as a solid begins acting more like a dense fluid. It liquefies. And once that happens, almost everything built on or inside it can move unpredictably. Heavy structures tilt. Foundations settle unevenly. Road surfaces deform. Buried tanks can rise. Pipelines tear apart. Buildings may remain structurally intact yet lean dramatically because the ground supporting one side drops away. Videos from liquefaction events around the world can look almost impossible. Pavement ripples, mud and water erupt through cracks, manholes push upward, entire houses tilt. Objects buried underground can float because the soil surrounding them is temporarily behaving like fluid. Now apply that process beneath industrial tanks containing enormous quantities of petroleum. Then keep shaking for several minutes. That is the scenario Portland faces. The soil underneath portions of the critical energy infrastructure hub represents almost exactly the kind of loose saturated sediment engineers worry about during earthquakes. A full Cascadia rupture could shake far longer than necessary to initiate widespread liquefaction. So while tanks are being pushed violently side to side by the earthquake, their foundations may simultaneously be losing strength. Inside each tank, thousands or millions of gallons of liquid are sloshing in the opposite direction. That internal motion creates enormous forces. Some tanks can buckle, others can rupture at welds, connections can snap, pipelines can pull apart, some structures may tilt as the ground beneath them deforms. Multiple failure mechanisms are happening together. According to modeling discussed in the source, an extreme event could release roughly half of the stored material across the hub. That would not be an ordinary industrial spill. It would represent an enormous petroleum release occurring in minutes. The source compares the potential volume to the Deepwater Horizon disaster. But there is an important difference. Deepwater Horizon released oil over an extended period into the Gulf of Mexico. A Cascadia fuel release could occur almost instantaneously beside an urban river. And Portland would simultaneously be dealing with an earthquake catastrophe. The fuel would not remain neatly inside the terminal. Once containment fails, gravity takes over. Liquid moves downhill. Some enters surrounding soil. Some moves across damaged industrial property. And enormous quantities could enter the Willamette River. The Willamette flows through Portland before joining the Columbia River. That means a large release does not disappear harmlessly into an isolated industrial channel. It enters a moving waterway passing through the city. Now add ignition sources. A magnitude 9 earthquake produces them everywhere. Downed power lines, damaged electrical equipment, broken transformers, ruptured natural gas systems, generators, vehicles, industrial machinery, sparks, open flames. A petroleum release spread across water does not need someone standing beside it with a match. It needs one successful ignition source. And after several minutes of destructive shaking, there may be hundreds. If fuel on the Willamette ignites, you no longer have a stationary refinery fire. You have burning material moving with the river. Flames travel downstream. Burning fuel collects against debris. Bridge supports can become exposed. Fire can reach structures along both sides. New sections of spilled petroleum continue feeding the flames. And the normal tools firefighters use may not work. Ordinary urban firefighting depends on several assumptions. The roads are usable. Hydrants contain water. Fire engines can reach the incident. Crews from unaffected neighboring communities can respond. Hospitals function. Communications work. A Cascadia earthquake potentially removes all of those assumptions at once. Water mains may rupture underground. Hydrants could be dry. Bridges could be damaged or closed. Liquefied roads may become impassable. Overpasses may collapse. Fire stations themselves can be damaged. Individual firefighters may be trying to locate their own families while simultaneously responding to citywide emergencies. Mutual aid works when one area is overwhelmed and surrounding areas remain functional. Cascadia could overwhelm entire regions together. One potential destination for a spreading urban fire is Forest Park. Portland's Forest Park contains thousands of acres of woodland extending across the city's west hills. Under dry conditions, it can become a major fuel source. If a Cascadia earthquake occurred during a warm, dry part of the year and fire reached the forest, tens of thousands of people living around the hills could face another emergency layered on top of everything else. The source estimates approximately 7,000 residents potentially exposed in the surrounding area. But again, evacuation cannot be assumed. Roads climbing through those neighborhoods may be blocked. Bridges elsewhere may be damaged. Emergency crews may not reach the area. Hydrants may have lost pressure. Residents may be attempting to leave at the same time that smoke and fire reduce visibility. There is an unsettling historical comparison. San Francisco, April 18, 1906. A massive earthquake struck the city. Buildings collapsed. Streets were damaged. But much of the ultimate destruction came from something that happened after the shaking. Fire. Gas lines ruptured. Ignition sources appeared. And crucially, the earthquake damaged water mains. Firefighters faced enormous fires without reliable water. The flames burned for days. Approximately 28000 buildings were destroyed. Thousands died across the broader catastrophe. More than a century later, Cascadia presents a similar basic equation. Major earthquake, broken water system, multiple ignitions, overwhelmed fire service. Except Portland adds another factor. An enormous percentage of Oregon's liquid fuel supply is concentrated along vulnerable riverbank soil inside the impact zone. But petroleum is not the only concern. This may be the least discussed part of the entire Cascadia scenario. Industrial facilities around Portland store hazardous chemicals. Some are flammable, others create a completely different danger. They become toxic gases. The source specifically mentions substances including anhydrous ammonia and chlorine. Anhydrous ammonia is widely used in refrigeration and industrial processes. When released at high concentration, it is extremely dangerous to the respiratory system. Exposure can injure the eyes and lungs and can become fatal. Chlorine gas presents another severe inhalation hazard. It was used as a chemical weapon during World War I for a reason. At sufficiently high concentrations, it can rapidly injure or kill people. Now imagine storage vessels containing these materials subjected to the same earthquake. The ground moves. Connection rupture. Storage systems fail. Electricity disappears. Automated safety equipment may stop working. Road access vanishes. And unlike fuel, toxic gas does not necessarily remain beside the damaged facility. Wind carries it. A plume forms. Then it moves across neighborhoods. The source describes hazard modeling focused on only 4 especially dangerous industrial sites. Under unfavorable conditions, that limited scenario alone produced more than 2,500 estimated fatalities from toxic exposure and potentially hundreds of thousands of people experiencing serious health effects. Only 4 facilities. The same broader analysis reportedly identified roughly 70 higher-risk chemical sites around Portland. And there is another problem. Emergency planners do not necessarily have a complete, perfectly detailed inventory describing every chemical, quantity, storage, condition, and vulnerability across every facility. That means uncertainty itself becomes part of the hazard. If planners do not know precisely what can be released, they cannot model every plume accurately. They cannot pre-position every response resource. They cannot tell every neighborhood exactly what it may face. And the people downwind could encounter the same obstacle we have already discussed. They may need to evacuate at the exact moment evacuation becomes physically impossible. Bridges are damaged. Roads are broken. Liquefaction blocks low-lying industrial corridors. Traffic signals are down. Communication networks are overloaded. Emergency vehicles cannot move. So the disaster creates both the reason to flee and the conditions that prevent people from fleeing. But there is another effect of Cascadia that receives even less attention. Some earthquake damage can be repaired. Buildings can be reconstructed. Bridges can eventually be replaced. Electrical systems can be restored. But part of the coastline itself may permanently change elevation. For centuries, tectonic compression along Cascadia has slowly distorted the edge of North America. As the offshore plate dives beneath the continent and the locked fault stores strain sections of coastal land are gradually warped upward. That deformation happens so slowly, people do not notice it. But when the megathrust finally ruptures, the elastic strain is released. Some areas of the coast can suddenly drop. Geologists call that process seismic subsidence. The source describes local subsidence potentially reaching as much as 6 feet. 6 feet, not over 100 years. In minutes. And once that land drops, it does not simply spring back to its previous elevation the next morning. The new position becomes part of the post-earthquake coastline. Imagine a coastal road sitting only 3 feet above high tide before the earthquake. Now lower the land 6 feet. That road is suddenly 3 feet below the old water level. A neighborhood that was technically outside a flood zone before breakfast can become permanently vulnerable to tidal flooding by afternoon. Wastewater facilities are especially exposed because treatment plants are often positioned on low ground near rivers or coastlines. Drop that infrastructure several feet while simultaneously damaging power pumps, pipes, roads, and seawalls, and the result becomes more than an earthquake problem. It becomes a long-term sanitation and contamination problem. Current modeling referenced in the source suggests Pacific Northwest coastal floodplains could expand by as much as approximately 115 square miles after a major Cascadia rupture. The number of buildings, roads, and residents exposed to coastal flooding could roughly double. The pre-earthquake map would no longer describe the actual coastline. Communities would have to rebuild around geography that had physically changed in minutes. And then another long-term process enters the equation: sea level rise. If Cascadia ruptures later this century, after additional ocean rise has already increased, coastal flood exposure sudden earthquake subsidence would occur on top of that higher baseline. The source suggests the combination could potentially triple exposure in some scenarios instead of merely doubling it. That is what makes compound hazards so dangerous. Neither process has to create the worst-case outcome by itself. The effects multiply. Rising seas gradually reduce elevation margins. Then one earthquake instantly removes several additional feet. Now, communities designed around historical sea levels suddenly occupy a different relationship with the ocean. At this point, you may reasonably ask how scientists can speak so confidently about an earthquake that has not happened in modern recorded history. The answer is extraordinary. We know when Cascadia last ruptured. Not merely the century. Scientists have reconstructed the date and approximate time. January 26th, 1700, roughly 9 o'clock at night. More than 325 years ago, there were no modern seismometers. There were no satellite observations. And indigenous oral histories preserved important accounts, but written instrumental records from the Northwest did not exist. The clue came from the other side of the Pacific Ocean, Japan. On that night, coastal communities in Japan experienced a tsunami. Water arrived unexpectedly and flooded low-lying areas. But something confused observers. Nobody had felt the earthquake that should have produced it. Normally, a locally generated Japanese tsunami is preceded by obvious shaking. This wave arrived without one. Historical writers documented what later became known as an orphan tsunami. A tsunami without an apparent parent earthquake. Centuries later, researchers revisited those records. They knew how quickly tsunami waves travel across the Pacific, so they worked backward. If the wave reached Japan at the recorded time, where would the source earthquake have needed to occur? The calculation pointed across the Pacific, toward North America, toward Cascadia. Then, researchers found physical evidence on the American side. Ghost forests. Along portions of the Pacific Northwest coast, stands of dead trees remain rooted inside tidal wetlands. The trunks are pale and weathered. Some have stood for centuries. Why did entire forests die at roughly the same time? Because the land beneath them dropped. Before the earthquake, the roots sat above regular saltwater inundation. Then a major Cascadia rupture caused coastal subsidence. The same land suddenly occupied a lower elevation. Saltwater flooded the root systems. The trees died. Scientists analyzed tree rings. The final growth occurred around the winter of 1699 to 1700. The Japanese historical record and the American forests independently pointed to the same event. One side of the ocean recorded the tsunami. The other side preserved the geological scar. Together, they allowed researchers to reconstruct an earthquake nobody measured directly. That history also reveals a much larger pattern. Over roughly the past 10000 years, Cascadia has experienced more than 40 major ruptures, according to the source. The spacing is irregular. Earthquakes do not follow a calendar. But recurrence intervals commonly fall within a range of a few hundred years. Roughly 200 to 500 years appears repeatedly in the geological record. We are now 325 years beyond the 1700 rupture. That does not mean Cascadia is overdue in the sense that a train is overdue. Faults do not follow schedules. But it does mean the region sits comfortably inside the broad recurrence range documented by previous events. Probability estimates cited in the source put the chance of a significant Cascadia earthquake during the next 50 years at roughly 1 in 3. The probability of the most extreme full margin event is described around 15% over that same period. Those numbers matter. A 1 in 3 chance across 50 years is not an abstract geological possibility millions of years away. It is a planning problem for people alive today. Infrastructure being built right now may still be operating during that 50-year window. Children attending elementary school today will still be alive. Homes receiving 30-year mortgages now may still be occupied. Bridges being repaired today may still be carrying traffic. That is why engineers and emergency planners cannot wait for certainty. There will never be a forecast saying Cascadia will rupture on a specific Tuesday next summer. Earthquake science cannot provide that. And that brings us to something else worth addressing. Every major earthquake topic attracts claims that scientists can secretly predict the event through solar activity, planetary alignments, unusual radio signals, or systems such as HAARP. The source is direct on this point. There is no scientific evidence supporting those claims as reliable earthquake prediction methods. Cascadia is being loaded by tectonic plate motion. The Juan de Fuca plate and North American plate are converging. Stress accumulates through geological mechanics. Solar storms do not meaningfully control that process. Planetary alignments do not create a usable earthquake timetable. Military radio facilities do not trigger megathrust ruptures. Focusing on unsupported theories can actually make preparedness worse because attention moves away from hazards we can measure and actions we can take. And there are actions available. For years, many emergency preparedness campaigns across the United States emphasized 72 hours of supplies. 3 days. That may be reasonable for some disasters. Cascadia is different. If roads, bridges, power, fuel distribution, communications, and water systems fail simultaneously, 3 days may be nowhere close to enough. The source notes that planners increasingly recommend at least 2 weeks of genuine household self-sufficiency inside the Cascadia impact zone. That means water. Enough for every person. Food that does not depend on refrigeration. A way to prepare or eat it without normal utility service. Medications. First aid. Lighting. Battery-powered communication. Backup batteries. Sanitation supplies. Warm clothing. Basic tools. And one resource people rarely include on emergency lists. Neighbors. In the first hours after a Cascadia earthquake, professional rescue teams may not be the first people reaching trapped residents. The first rescuers may be whoever lives next door. The first medical help may come from someone on the same street. The first welfare checks may happen between households. The first debris removal may be performed by residents with gloves, crowbars, and shovels. Community connections become infrastructure when normal infrastructure disappears. And there are larger decisions that cannot be solved by individuals. The petroleum tanks at Portland's critical energy infrastructure hub can be strengthened. Foundations can be improved. Pipelines can be given better seismic flexibility. Old bridges can be retrofitted or replaced. Water networks can be segmented so one break does not collapse the entire system. Chemical storage facilities can be better inventoried. Hazardous materials can be relocated or hardened. Emergency routes can be reinforced. The region is not powerless. The uncomfortable truth is that much of this work is expensive, slow, and incomplete. And Cascadia does not care about infrastructure budgets. The fault has been accumulating stress for centuries. When it eventually ruptures, the shaking will probably dominate the images everyone remembers. Collapsed structures, moving roads, tsunami footage. But years later, the defining story may be everything the earthquake triggered. The fuel release, the fires, the toxic plume, the months without reliable electricity, the destroyed transportation network, the coastline permanently sitting lower than it did that morning. The earthquake itself is the trigger. What society has placed around that trigger determines how much of the catastrophe happens afterward. But there is one more dimension that deserves attention. The rescue timeline. After most major American disasters, outside assistance starts moving toward the affected region very quickly. FEMA urban search and rescue teams, National Guard units, medical personnel, utility crews, food, water, generators, heavy equipment, fuel. The entire American disaster response system is built around moving resources from functioning regions into the disaster zone. That system works because most disasters leave at least some external transportation network intact. After a major hurricane, trucks can often drive from neighboring states. After a tornado destroys a city, highways 20 miles away may remain completely functional. Aircraft can reach airports outside the damage corridor. Fire departments from nearby counties can travel toward the emergency. Cascadia threatens those assumptions. A full rupture could damage the physical connections needed to bring assistance into the Pacific Northwest. Major Columbia River crossings may fail or become unsafe. Highway bridges across Oregon and Washington include large numbers of older structures built before modern seismic design. The source references a 2019 Oregon Department of Transportation assessment indicating that much of the state's bridge inventory was designed under older standards and that many crossings could become impassable after a Cascadia event. That changes everything. Imagine emergency supplies sitting safely east of the mountains. Now imagine the bridges needed to carry them west are damaged. Mountain routes contain landslides. Overpasses fail. Fuel is unavailable. Road surfaces crack. Travel times explode. Portland International Airport presents another problem. The airport sits on low, potentially liquefiable ground near the same broad river corridor as the fuel infrastructure. If runways deform or supporting systems fail, the airport may not immediately function as the giant relief gateway everyone would naturally expect. Then consider the Port of Portland. Normally, a functioning port would provide one of the most efficient ways to move large quantities of fuel, food, construction, equipment, and emergency supplies into a damaged region. But the port occupies the same river environment exposed to liquefaction, industrial spills, fires, bridge failures, and debris. The natural entry points for rescue are themselves inside the disaster. That is what makes Cascadia unusual compared with many other American emergencies. After Hurricane Katrina, outside states still had intact highway systems. Help could move toward Louisiana from outside the hardest-hit area. After the Joplin tornado, emergency crews traveled toward the city using roads that had not all been destroyed across several states. A Cascadia rupture would affect an enormous geographic region at once. Northern California, Oregon, Washington, British Columbia, coastal communities, major metropolitan areas, mountain transportation corridors. The disaster zone is not one city. It is a region, and roads approaching from the east must cross mountainous terrain containing bridges and slopes vulnerable to earthquake damage. Approaches from the west do not exist. that is the Pacific Ocean. Approaches from north and south may cross the same damaged transportation systems. That means the federal response may encounter a problem that cannot be solved merely by having more trucks. You can have 10,000 relief vehicles. They are useless if no reliable road connects them to the people who need supplies. You can have cargo aircraft. They require usable runways. You can have ships carrying enormous amounts of equipment. They require ports where cargo can be unloaded and transported inland. The response does not struggle because agencies suddenly forget how to respond. It struggles because the earthquake physically removes the pathways that response depends upon. Internal planning scenarios described in the source use unusually severe language. A full Cascadia event could exceed state and local response capacity. It could strain federal resources beyond previous domestic disasters. Basic recovery may take years. Complete regional economic recovery could take a decade or longer. Again, this is not a prediction of exactly what every town will experience. Not every bridge fails. Not every utility remains offline for 12 months. Not every community sees the same shaking. But large-scale planning has to be built around the possibility that outside help will arrive more slowly than people expect. That is why 2 weeks of supplies is not simply an extra comfortable emergency kit. For many households, it could represent the minimum period during which they need to function largely without normal systems. Think specifically about water. Humans can survive without electricity. They can survive without internet. They cannot survive long without water. If municipal pipes break and treatment plants lose electricity, the faucet may stop working. 2 weeks of water for several people occupies real space. It requires planning. If you take medication for a chronic condition, ask what happens when the local pharmacy is closed and roads are impassable. If your food supply depends entirely on an electric refrigerator, ask what happens after the first day without power. If you live in an apartment and the elevator stops, ask how you move supplies upstairs. If your family members are spread across Portland or Seattle, decide where everyone attempts to reunite. Do not assume phones will work. Create an out-of-area contact. Learn basic first aid. Keep sturdy shoes beside the bed. After a major earthquake, broken glass may cover the floor before you ever stand up. Secure tall furniture. Strap water heaters. Know how to turn utilities off if authorities instruct you to do so. Keep fire extinguishers where they are accessible. Those actions sound small compared with a magnitude 9 earthquake. But preparedness works by solving thousands of small problems before they all arrive at once. The Cascadia Fault has remained quiet since January 26, 1700. For human beings, 325 years feels almost unimaginable. For geology, it is brief. The ghost forests along the coast are still there. Dead trunks standing inside tidal wetlands where living forests once grew above the saltwater line. They are physical evidence that the coastline has dropped before. The Japanese records are still there. Written descriptions of a tsunami that crossed an entire ocean from an earthquake nobody in Japan felt. The geological layers offshore are still there. Deposits left by previous Cascadia earthquakes and tsunamis stretching thousands of years into the past. All of them tell the same story. This fault repeatedly stores stress. Then it ruptures. Then the Pacific Northwest changes. The next rupture will happen in a world completely different from the one that existed in 1700. Portland did not exist as the city we know. Seattle did not exist. Modern ports did not exist. Fuel farms did not exist. Chemical plants did not exist. Interstate highways did not exist. Millions of people did not live inside the impact region. The geology is ancient. The vulnerability is modern. That is the key distinction. Cascadia itself has not suddenly become dangerous because people discovered it. It has always been capable of enormous earthquakes. What has changed is everything human beings built above and beside it. We concentrated 90% of one state's liquid fuel distribution on vulnerable river sediment. We built highways and bridges before modern seismic understanding. We placed industrial chemicals near population centers. We developed coastal neighborhoods only feet above sea level. We became dependent on electrical communications, water, and supply networks that work brilliantly when they are connected and become liabilities when every connection fails simultaneously. That is why the biggest Cascadia question is not whether geology can produce the earthquake. The historical record has already answered that. The question is how much vulnerability we choose to leave in place before the next one. Nobody watching this video can decide when the Juan de Fuca plate finally slips. Nobody can release the accumulated strain safely. Nobody can stop the tsunami. But communities can decide whether fuel tanks remain sitting on foundations known to be vulnerable. States can decide which bridges get retrofitted first. Cities can map chemical hazards. Utilities can harden water systems. Hospitals can increase backup capacity. Neighborhoods can organize response teams. Households can prepare enough water and food to survive the first days without outside help. People can learn whether they live inside a tsunami evacuation zone. Coastal residents can understand that after strong shaking, waiting for an official alert before moving inland may cost critical time. The earthquake is unavoidable. Many of the secondary consequences are not completely unavoidable. That is why this story matters now rather than after the rupture. Afterward, every weakness becomes obvious. The broken tank was obviously vulnerable. The bridge obviously needed strengthening. The neighborhood obviously needed an evacuation plan. The chemical inventory obviously should have been mapped. The household obviously needed more water. Disasters make preparation failures look obvious after the fact. The difficult work is seeing them before. So let us put the scenario together one final time. The Cascadia megathrust breaks. Hundreds of miles of fault begin moving. The shaking continues for minutes. On the outer coast, people who can still move begin heading toward high ground because the tsunami may arrive quickly. Inside Portland and Seattle, older buildings are damaged. Brick facades collapse. Bridges are inspected or fail. Power disappears. Waterman rupture. Communications overload. Along the Willamette River, saturated industrial soil begins liquefying. Large storage tanks to form. Some rupture. Pipelines separate. Fuel flows. A major portion enters the river. One ignition source is enough. Fire begins moving with the current through a city where hydrants may already be dry. Other industrial facilities release hazardous chemicals. The wind carries the plume toward populated neighborhoods. Residents receive orders to move, but damaged streets and bridges make evacuation difficult. Fire reaches vegetation. Emergency agencies try to respond across a region where every jurisdiction is overwhelmed. Meanwhile, the coastline has dropped. Areas hit by the tsunami do not simply rebuild at the same elevation afterward. Some communities discover that their relationship with the ocean has changed permanently. Airports and ports needed for relief may be damaged. Outside rescue teams begin moving toward the Pacific Northwest but encounter failed transportation routes. Neighbors become the first responders. Days pass. Then weeks. Power returns unevenly. Water remains unreliable in some areas. Fuel distribution becomes a massive logistical challenge because the very hub that supplied the region has been destroyed. Recovery continues for months. For some infrastructure years, that is the Cascadia disaster researchers are trying to prepare for. Not simply one giant earthquake, a cascade. One failure triggering another. Shaking causing liquefaction, liquefaction causing industrial failure. Industrial failure causing fire and chemical release. Broken water mains making the fire harder to stop. Damaged roads trapping both emergency crews and residents. Subsidence creating permanent flooding problems. Transportation failure slowing outside aid. Everything connected. And that is why focusing exclusively on earthquake magnitude misses the most important point. Magnitude describes how much energy the fault releases. It does not describe what society has placed in the path of that energy. A magnitude 9 earthquake under an uninhabited landscape is one thing. A magnitude 9 event affecting modern cities dependent on fragile infrastructure is something else entirely. The fault does not know there are petroleum tanks beside the Willamette. It does not know 70 high-risk chemical facilities exist around Portland. It does not know millions of people depend on bridges crossing rivers. It does not know wastewater treatment plants occupy low coastal ground. It does not know people expect grocery stores to reopen within days. It knows only tectonic stress, and that stress continues, accumulating whether society prepares or not. So, if you live in the Cascadia impact region, do not walk away from this frightened. Walk away with a list. Find out whether your home is in a tsunami zone. If it is, know the route to high ground. Do not assume you will have a car. After a major earthquake, roads may be unusable. Know the walking route. Store water. Store food. Keep essential medications available. Prepare for more than 72 hours. Know your neighbors. Secure heavy objects. Learn basic first aid. Have battery-powered or hand-crank communication equipment. Keep shoes, gloves, and flashlights where you can reach them, even if furniture has fallen. Talk to your family about where you will meet if phones stop working. And pay attention to local emergency management guidance. For governments and industries, the checklist is larger. Strengthen the fuel hub. Retrofit bridges. Harden pipelines. Improve emergency water systems. Map hazardous chemicals completely. Increase port and airport resilience. Develop alternative logistics routes. Build neighborhood-level response capacity. Prepare for a coastline that may physically drop after the earthquake. Because once Cascadia finally moves, nobody gets another 325-year preparation window. The rupture itself may take only minutes. The consequences could last generations. And that is ultimately the part of Cascadia that deserves far more attention. The earthquake will be terrifying. The tsunami will be devastating. But those events are only the beginning. The river that may burn afterward. The toxic plume that may move through neighborhoods afterward. The people who cannot evacuate afterward, the months without dependable electricity, the supply chains cut apart, the coastline permanently lower than it was that morning. Those may define the disaster long after everyone stops talking about the shaking. Cascadia is the trigger. Everything built around that trigger is still something human beings can change. And right now, before the ground moves, is the only time that work can be done. Subscribe if you want more investigations like this one. Leave a comment telling me which part of this scenario surprised you most. And share this with someone living in Oregon, Washington, Northern California, or coastal British Columbia. Because this is information people need before Cascadia ruptures. Not afterward. The fault has been silent for 325 years. The ghost forests remember the last earthquake. The Japanese tsunami records remember it. The seafloor remembers it. And beneath the Pacific Northwest, the plates are still moving. Stay informed. Prepare for what you can control. And I will see you in the next one.